Welcome to today's section. So today we will study about isomerism shown by coordination complexes. What is meant by isomerism? As we all know that isomerism is the phenomenon of existence of compounds with same molecular formula and different structural formula. Like organic compounds, coordination complexes also exhibit different type of isomerism. The isomerism exhibited by coordination complexes are classified into two different types, that is structural isomerism and stereoisomerism. Structural isomerism means they have same molecular formula but their structural arrangement, that their bonding will be different. So molecules with the same molecular formula, different structural arrangement are called structural isomers, and that phenomenon is called structural isomerism. But in stereoisomerism, molecular formula will be same, structural formula will be same, that means they are bonding, there is no change in their bonding, but there is only difference in orientation of atom. So stereoisomers arises due to the difference in orientation of atoms. They have same molecular and same structural formula. There are four different types of structural isomerisms are shown by coordination complexes. They are, first one is linkage isomerism. Second one, ionization isomerism. Third one, hydrate or solvate isomerism. And the last one is coordination isomers, or we can call coordination position isomers. These are the four structural isomerism shown by coordination complexes. Then there are two types of stereoisomerism shown by coordination complex. They are geometrical isomerism and optical isomerism. So now we will discuss each one in detail. First we will discuss about the linkage isomerism. This is the first example of structural isomerism. Linkage isomerism is shown by coordination complexes with ambidentate ligand. What is meant by ambidentate ligand? A ligand which can attach using two different atoms. That type of ligands are called ambidentate ligands, that we already discussed. Examples are cyanate, thiocyanate, NO2. Here you can attach using Cn or NC, NCSSCN. This can attach using ONO and NO2, two different atoms. So complexes containing this type of ligands, that is called ambidentate ligands, will show linkage isomerism. For example, I will name this compound. You know that cyanide is -1, so -6. Here is +1, so complex charge is -3. Here is X, so X -6 is equal to -3, X is equal to +3. So its oxidation state is +3. How will you name this compound? It is potassium hexacyanocobaltate, because it is a negative complex. Potassium hexacyanocobaltate. Then in bracket you have to write the oxidation state in Roman numerals. That is the name of that compound. Then using the same molecular formula we can write another molecule. K3CO NC6. Everything is same, but only the difference is Here the carbon it is attached to the cobalt, but here nitrogen is attached to the cobalt. So there is difference in bonding to the central metal atom, or there is the difference in linked atom. That is why it is called the linkage isomerism. What's the name of this one? This is potassium hexa. This ligand is called isocyano. This is cyano and this is isocyano. Potassium hexa isocyano cobaltate 3. I will write the name. Potassium hexa isocyano cobaltate 3. This is potassium hexa cyano, only the difference in only this iso. Cyano cobaltate 3. So these are the examples of linkage isomerism. So linkage isomerism is shown by coordination complexes which contain ambidentate ligand that differs in only the linked atom to the central metal atom. So isomerism which differs in linked atom to the or bonded atom to the central metal atom, that type of isomerism is called the linkage isomerism. It is usually shown by coordination complexes with ambidentate ligand. Then second one, that is called ionization isomerism. Ionization isomers differs in the ions which are produced by the dissociation of coordination complexes in solution. We know that when we dissolve coordination complexes in water, the ions which are outside the bracket, outside the coordination sphere, will undergo ionization. For example, CO, can take Cr, NH3 5 times Br SO4. What is the name of this complex? Here also the oxidation state of chromium is +3 because sulfate charge -2. So complex charge is +2. Ammonium 0, -1. So X -1 is equal to +2. So X is equal to +3. So this oxidation state of chromium is +3. Its name, there are 5 amines. So pentamine, bromo, chromium 3 sulfate. Pentamine, bromo, chromium 3 sulfate. Here if we dissolve this complex in water, that is ionization. It will undergo ionization by dissolving in water. We will get 2 ions. One is the square bracket and the inside one CONH3 5 times Br +2 and SO4 2-. So here when we add barium chloride to that solution, we will get a white precipitate due to the presence of sulfate ion, because they are producing sulfate ions in solution during ionization. So using this same formula, you can write another one. Cr NH3 5 times SO4 Br. The difference is there is exchange of the bromine and sulfate inside and outside. So as a result, this on dissociation will get bromide ions in solution. So if you add barium chloride, we will not get the white precipitate, but we can find the presence of bromide ions by using another solution. That means these two have same molecular formula because they are 1 Cr, 5 amine, 1 bromine, 1 sulfate. And its name is pentamine, sulfato, chromium 3 bromide. Pentamine, sulfato, chromium 3 bromide. But the only difference is there is difference in the ions which are produced during ionization in solution. So isomers which differs in the ions which are produced during ionization are called ionization isomers. They have same molecular formula but they have difference in the ions produced during ionization. So that type of isomers are called ionization isomers, and that phenomenon is called ionization isomerism. And third one is solvate isomerism, or we can call it solvation. Solvate or hydrate or hydration. Hydrate isomerism. It is usually shown by coordination compounds in which water is one of the ligand. Example, what is the name? Here also oxidation state is +3. So water is called aqua hexa. It is 6 times. It is called hexa aqua cobalt 3 chloride. That is a name. Then using the same I can write one more CO H2O 5 times Cl. Always the coordination number will be 6. So here 5 water, that means 1 chloride will be inside. Outside only 2 chloride and dot H2O because it is hydrated. What is the name of this? It is penta aqua, only 5 water, so it is penta aqua chloro cobalt 3 chloride monohydrate, because there is only one water molecule outside, so it is called a monohydrate. Penta aqua chloro cobalt 3 chloride monohydrate. So these two have the same molecular formula. They differs only in the water molecule inside and outside of the coordination sphere. That type of isomerism is called solvate. We are always using water as the solvent, that is why it is called a hydrate isomerism. So you can write more examples using the same formula. COH2O 4 times. We are again reducing one more water, and so we are making inside 1 chlorine. Total coordination number always will be 6 for cobalt, and outside there is only 1 chlorine remaining, dot 2 H2O. There are 2 water molecules outside the coordination sphere. So its name is 4. It is tetra aqua dichloro cobalt 3 chloride dihydrate. Tetra aqua dichloro cobalt 3 chloride dihydrate. We can write one more example. COH2O 3 times Cl3. Total coordination number is 6. There is no chlorine outside because only there are 3 chlorine. We make it inside. So remaining there is 3 H2O. So its name is triaqua. There is 3 aqua, triaqua, trichloro, cobalt 3 trihydrate. So these are the examples of hydrate isomers. So hydration isomerism or solvation isomerism is shown by complexes which differs in the water molecule inside and outside of the coordination sphere. Then the last one in structural isomerism is coordination isomerism. Coordination isomerism is shown only by double complex. That means positive part and negative part are complexes. That type of complexes are only shown by this type of isomerism. Example CN6CONH36. Here cyanide is linked to chromium and here amine is linked to cobalt. So if we exchange the ligands, that is the position of coordination will change and we'll get coordination position isomerism. CrNH3 6 times CO Cn 6 times. This is an example for coordination isomerism. It is shown by always by double complexes. That means a positive part and negative part are complexes, and the coordination number of the two metal atom must be same. That type of complexes are shown by coordination. How will you name this? You can name. I will have to assign one of the oxidation state, then only we can find the other one. So this -3, it is a positive negative part, and 0, and this is a positive part. You have to name the positive part first. So this is a positive complex. So first hexaamine cobalt 3, hexaamine cobalt 3, hexacyanochromate, because it is a negative complex, chromate, that is the name, chromate in bracket 3. And here +3, this -3. So the name, here the positive part is this one. So we have to name this first. Hexaamine chromium 3. Hexaamine chromium 3. Hexacyanocobaltate 3. That is the name of this complex. So these are the different type of structural isomerism shown by coordination complexes. They are linkage, ionization, solvate, coordination, isomerism. Next we will discuss about the geometrical isomerism, that is a stereo isomerism shown by coordination complexes. So there are two types of stereo isomerism. First one is geometrical isomerism. Geometrical isomerism. Normally in organic compounds, geometrical isomerism arises due to the restricted rotation about the carbon-carbon atoms. Here also there is a restricted rotation, but not like organic compounds. So there are two types of complexes, that is tetrahedral complexes and octahedral complexes. Tetrahedral means coordination number coordination number 4, and octahedral is coordination number is 6. These two types will also show geometrical isomerism. First one, tetrahedral complexes. Tetrahedral complexes means the ligands number will be 4. Example, M type Ma2B2, this type of complexes. That means this is a metal, 2 different type of ligands, total 4 ligands. This type of complexes, that is complexes with the general formula Ma2B2. M is the metal and these two are ligands, and they must be different. If they are same, they will not show geometrical isomerism. So this is square planar complexes. Shape is square planar and central atom is metal. Then we can arrange the ligands A, B, B. And draw one more structure. Same molecular formula M, A, B, B. Here in the first structure, we can see that the same type of ligands, that is A and A, are on the same side, or B and B are on the same side. That type of geometrical isomerism are called cis isomerism. So here we are discussing geometrical isomerism. They are called also cis trans isomerism. Different type. One of the example is cis trans isomerism. So if the ligands, same type of ligands are on the same side of the complex, that is called a cis isomer. And here A and A are on opposite side. They are not on the same side. So different ligands are on the same side. So that is called a trans isomer. So if ligands, same type of ligands are on same side of the square planar complexes, that is called a cis isomer. If same type of ligands are on the different type of complex, it is called a trans isomer. A very good example is a medicine which is used for the treatment of cancer, that is called cisplatin. I will write the structure, that is PT NH3 twice Cl2. How will you name this? Oxidation state is +2. Diamine dichloroplatinum. Diamine dichloroplatinum. So here, instead of M we can write platinum, and instead of A, NH3, and instead of B we can write chlorine. So this is a cis isomer of this complex, and its common name is cisplatin, and it is an anti-cancer drug. It is an very famous anti-cancer drug. But the difference, if it is in trans, it does not have the medicinal property. Instead, it is very toxic compound. That is, trans isomer is very toxic. That is, there is a very large difference between the properties of cis and trans isomer. Platinum, NH3, Cl, Cl. This is called a transplatin because both amines are on different side, both chlorine are on different side, and this is not a drug. It is a drug or it is a medicine, but it is very toxic. That means it is highly poisonous. So this is the first example. Geometrical isomerism are shown by tetrahedral complexes with the gel formula Ma2B2. So not of tetrahedral square planar complexes. There are two different type of ligands. One very good example is diamine diacoplatinum. Its cis isomer is very good for anti-cancer. So it is an anti-cancer medicine, and trans isomer is highly poisonous. Another example. It is not in tetrahedral, square planar. Next is octahedral complexes. Octahedral complexes means ligands number must be 6. Of the formula Ma4B2. There are two types of ligands, Ma4B2 or MAA twice. AA means it is a didentate ligand. B2. That's 2 into 2 is 4. We'll write an example. CO NH3 4 times Cl2. I've drawn this cis and trans isomer. We can draw octahedral very easily. First draw a square and one above the plane and one below the plane. If we join all these corners, we will get an octahedron. I am not drawing that because it will be very confusing when we draw. So here central atom is cobalt, NH3, NH3. The all remaining, NH3 4 times, 1, 2, 3, 4. Cl, Cl. Here, both chlorine are on the same side. So this is an example for cis isomer. So this is cis tetraamine dichlorocobalt 2. Then I will draw the trans isomer 2. In trans isomer, chlorine are on the different side of the octahedron. One above the plane and one below the plane. This is an example for trans isomer. So CONH3 4 times Cl2, that is an example for Ma4B2. That Ma4B2. It can show cis and trans isomerism. In cis isomers, the same ligands are on the same side. If the same ligands are on the different side, that is called a trans. Then we can write another example using a didentate ligand. Example, CO. Can you name one didentate ligand? Ethylene diamine. The short form is EN. EN twice Cl2. We can say use the same. So it is a didentate ligand.